Pressure sensing usually entails three stages: a sensing element translating pressure into a mechanical displacement of a flexible part, a transducer converting mechanical displacement into an electrical effect, either modifying resistance or creating a small voltage or current. Electronics are used for signal conditioning. This may entail modifying a nonlinear signal or may convert an analog output to a digital output. Pressure sensors are increasingly taking the form of microelectrical mechanical systems, all three stages combined on one silicon chip. We have absolute pressure, gauge pressure, differential pressure. Absolute pressure, we have a dynamic pressure working against a vacuum. Gauge pressure, we have a dynamic pressure working against atmospheric pressure, 14.7 psi. Differential pressure, we have two dynamic pressures working against each other where we take the difference. This is a snapshot of what we're working with today. It's advertised as having a plus or minus 2% accuracy, full scale, stainless steel body, ceramic pressure chip, surge protection, lightweight, widely used in oil tank, gas tank, and diesel tanks to detect oil, fuel, diesel, gas, or water pressure. Absolute pressure sensor here, used to measure pressure with reference to a vacuum, which would normally be used in something like a manifold pressure, as opposed to fuel or oil pressure, where we'd be using more pressure reference to the atmosphere, or 14.7 psi. Absolute pressure output is calibrated to be proportional to the difference between applied pressure and a fixed reference, a perfect vacuum. Sealed gauge, the output is calibrated to be proportional to the difference between applied pressure and a reference of one standard atmosphere, 1013 bars or 14.7 psi. The absolute at 0.5 for reference to a vacuum. On the gauge pressure at 0.5 volts for reference to atmospheric pressure, 14.7. Our voltage systems are 5 volts, 3 volt system. On our 5 volt system, we're going to be scaling from 0.5 volts DC to 4.5 volts DC. On our 3 volt system, 3.3 volt system, we'll be referencing or scaling between 0.33 volts DC and 2.97 volts DC. There are also out there in a lot of industrial applications 4 milliamp to 20 milliamp current loop systems. We'll talk about those at some later date. Here's a diagram of the chip, our silicon chip, our die, where we have etched into that die piezoelectric elements, and we have a diaphragm and a cavity, which would be either vacuum or psi pressure, atmospheric pressure, 14.7 psi is our reference against the diaphragm movement. Here we have a resistive bridge network. It could be a resistive bridge or some other type of resistive network where the distortion by the pressure forces a change in the resistance of the piezoelectric elements. And the sensor we'll be dealing with today, here's the output characteristic. It's advertised as being linear from 0.5 to 4.5, where 0 psi is 0.5 volts, 50 psi 2.5 volts, and 100 psi 4.5 volts. We have our test bed ready to go for testing this sensor to verify its output. We have a portable compressor. We have a power supply that's going to supply 5 volts to the sensor. We have a meter to measure the sensor's output. Just regular tubing. We're going to pressurize it. It's not holding much volume of air, but it should come up to pressure fairly quickly. and then we'll take the measurements and plot those measurements and make sure it complies with what the manufacturer says. It's linear from 0.5 at 0 psi up to 4.5 volts at 100 psi. Now that we have our data points, we're going to plot them out and determine an equation for our Arduino so we can obtain a correct pressure readout from our sensor. So we'll go to Stats, Edit. We're going to edit our values for X and Y. I already have them entered. These are the values we obtained during our test. So we're going to go and Y equals, that should be clear. Make sure that's clear, there's no other equation in there. Our stat plotter is on. Scatter plot has been selected. Back to stats. Well, first let's look at the data. Since we have a list of data here that shows what we obtained, let's see how that lines up. We'll look at graph at the data points. Those are all 10 of the data points. They line up almost perfectly on a straight line. So let's plot that out and get our equation. Go back to stats, and we're going to go over to calculate, and we have a list of about 10 other types of regression charts that you can do. We're going to do a linear regression later on when we do some work with thermistors, which is more polynomial or exponential. We can choose the correct chart for that, but for now we're going to choose linear regression calculations. Number 4. Our X list is Y1, our Y list is Y2. Frequency list, we're going to store the equation in Y equals. So we'll go over to variable, Y, function. We're going to get a function there we're going to create. I'm going to put it in Y1. Okay, we're ready to calculate. Move down to calculate. Enter. That's our equation for Y, for a linear regression or straight line equation. A is essentially our slope of the line. 0.040 looks like rounded off. Our B value 0.47, and this is a correlation calculation that gives us essentially 99.9% of our data points are represented by this equation. That's what it's telling us, kind of how close we were when you could. Let's take a look at it, matter of fact, and see how close we were. They mostly all line up almost perfectly, all 10 data points, so it's a very linear output from that sensor. The code's loaded, so now we'll proceed with the demonstration of an industrial pressure sensor interfaced with an Arduino. Right now we're sitting at a 0 psi. We're going to bring it up to 30, and we're going to work our way up to 100 psi and see how the Arduino tracks the pressure changes. Okay, I kind of overshot it, 41.5, so let's see what it does. 41 on the pressure gauge, 41 on the Arduino. Okay, let's take it up to 60. So 50. We'll 50 first. And 56 is where it stopped. 56 on the pressure gauge, 56 on the Arduino. Let's go up to 70 something. $76. at 82. Okay, see how it does 82 then. We've got such a small volume of air, it kind of overshoots most of the time. So 81.5, Arduino 81. Okay, we'll try to shoot at 100. Might be a little slight leak, it seems to bleed off, and that's 105. Kind of overshot, 105 on the pressure, 104 on the pressure gauge now. 104 on the Arduino. It'll slowly kind of bleed off, it looks like. It's down to 103 now. 103 on the Arduino. Release all the pressure. Well, 0. Performed pretty well, did pretty good. Based on the ADC's performance and everything else, that's pretty good. Here we have it plotted out. We have on the lower end at 0 psi, we have 0.5 volts. At the upper end, measured, most of the sensors, they show 4.5, but in actuality, this is what we entered, 4.6. So we're going to do the equation for that number. We're going to start out at 0 psi, 0.5, 100 psi, 4.6. And this is our linear line, perfect linear line. Whether the sensor is perfectly linear, it's not. So there's a little bit of variation. But we have our x-axis, our voltage, which is our input range, or what they refer to the domain. And we have the range, our psi, our y-axis. So in order to write an equation, we need 2 points. So we're going to kind of write that in here, x, y. Coordinates for us that we do have, 0.5x, which is our independent range. This is a dependent range, the y-axis. Then we have 4.6 at 100. First thing we need to do is we need to find out the slope of the line, since we have the 2 points. And the slope of the line is represented by m, which is the change in y over the change in x, equals y2 minus y1 over x2 minus x1. In this case, we're going to take these 2 points, our y2, x2, y2, that's a 4.6, 100. Our x1, y1 are the lower ends, the 0.5, 0 psi. So we're going to plug that in to our equation. So our y2 is 100. That should be y2 here. y2 is 100 minus y1, which is 0, over x2. x2 is 4.6 minus x1, which is 0.5. Okay, and when we do the math for that, we end up with 100 divided by 4.1 gives us 24.3902 for our slope. So m equals that. And now there's 2 representations of a line, the forms of a line, a linear line. There's the y-intercept form of the line, which most people recognize is this is probably the one that you mostly see is mx plus b, equation for the line. If you know the slope and b, which is the y-intercept, that is where the line crosses the y-axis when x is 0. Since it crosses down here somewhere, but we really don't have that point, so we have to fall back to the other form of a line, which is represented by y2 equals m onto x2 minus x1 plus y1. So at this point, what we're going to do is we're just going to pick a point on the line, any point. We could pick this point or we could pick this point. But since it's the easier math, 0.5 and a 0, we're going to use that as we plug in for the x1, y1. So we're going to rewrite this since we have the slope y2 equals 24.3902 times x2 minus, since we have a point now, we're going to, x1 is 0.5 plus, for y1 is 0. So that makes that easy. That falls out. As we do the multiplication, y2 equals 24.3902 x2 minus, now we're going to multiply that times that, and that's going to give us minus 12.1951. And since this is 0 plus 0, so we'll just leave that's essentially our equation. So we can replace these y's. And what's the y? The y is the psi. Psi equals 24.3902. What's x2? Well, x2 would be the voltage that we read from the Arduino. So we could say times volts minus 12.1951, and that's our equation for the line. You could also figure that out. You could do that on Excel or a graphics calculator. You can also figure it out. And by the way, that formula, this form of the line, this is called the Pointslope form of a line. That's actually your map equation, your map function in Arduino. When you enter those numbers, you're actually entering this equation. That's that equation expanded, where m is already the y2 minus y1, x2 minus 1, which is the input-output. And if you look at the mapping function in Arduino, that's essentially that equation. So that's what you're doing. And it works for any type of scaling you're doing, like the TMP 36 temperature sensor. It has that 0.5, what they call an offset. But when you do the equation, you don't have to worry about any offset. You're not worried about 0.5 offset, because the equation will take care of that. You just enter the numbers, and the offset is that's offset back from 0.5. But actually, no, this is actually the offset, the y-intercept, because that's when x is 0. That's where y lies. So some people might confuse this b here with 0.5 as an offset. No, this is the y-intercept is what that b stands for. And also we did one for this is for the every 5-volt system. nano every. We did that one, and we won't go through the math, but for the maker 1010110, which is kind of the same thing, the same procedure. Find the slope, point slope formula, the math, and just with a few steps we have our scaling. And like I said, that works for any type of scaling you're going to do with a microcontrollers. Usually you can do it with that equation, or Excel or a graphics calculator. You could have done the same thing and it would give us the same result as you have here. Let's now take a quick look at the code. We're going to include some libraries here. The SPI wired library, the Adafruit graphics library, the Adafruit OLED library, SSD 1306. We're going to set up some variables for the OLED, screen width, screen height, reset pin. We're going to default that to one of the unused pins on the Arduino. The address for the OLED. Going to set up a variable for our sensor pin. Going to set up a variable for our alpha for our low pass filter, which we'll discuss when we get there, that line in the code. We're going to set up an AREF, which is our analog reference measured. We're going to actually measure what our analog reference is. In most cases, when you're dealing with an Arduino, depending on how it's powered, you won't actually have 5 volts. You'll have something less than 5 volts. It could be 4.6, 4.7. But in most cases, if you're powering it off your computer, it's less than 5 volts. So you should always measure it and take that reading and use that in your calculation to determine the voltage. That's what we'll do here. We'll see that line when we get down to a couple lines lower. The starting point for our low pass filter that we're going to implement, we start at the midpoint of the 1024 readings. Just have to start somewhere when you first initially start. Sensor valve, this is where we're going to store our value for our sensor valve, what we get back from the analog read. Our voltage, PSI, we stored in those variables. Our Adafruit sensor, this creates our instance of the Adafruit sensor, OLED sensor. We're going to give it the screen width, screen height information, the reset pin, and we're going to give it a reference to the wire library. This is a pointer to a variable that's going to pass data from the library to the sensor functions that make up this Adafruit library for the OLED display. Now we're going to go in our setup. We're going to set up our serial monitor. We're going to check and see when the serial monitor is ready. We've commented out these lines. We're not using any external internal references. We're using the reference 4.6 that we're going to use, or the internal 5 volt reference. And then we go to information that we're setting up for the sensor. It's going to check and see if it's there. If it's not, it's going to give us an error and go into a while loop, and it's going to sit there until we correct that and make sure our OLED sensor is connected. We're going to do a clear display, display. Then we're going to go into the loop. We're going to do an analog read of the pressure sensor, which is on A0. We're going to put it in the sensor valve. Then we're going to take that information, sensor valve, and our prior reading into our low pass filter, which is essentially a way of running an average of your current value to your incoming values. So we're taking a portion, 95% of this value, our current values, to 5% of the incoming readings, and we're averaging to get them a running average in this proportion, which was going to eliminate all those fluctuations in your reading. Then we're going to take the filtered valve, after it's filtered, We get a good reading, we're going to put it into the equation and we're going to determine the voltage. And this is where we have our AREF, our actual measured analog reference. Then we're going to determine here on this line with that formula which we derived in the video to get a PSI reading, which is the actual PSI at the sensor. Then we're going to take that information to do a serial print to the serial monitor for troubleshooting. Then we're going to update the OLED with this function, which is this function here that updates the OLED. And then we're going to delay for 200 milliseconds and we're going to start the loop over again.